All right, welcome everyone to day 3 of our common envelope meeting. So before we start our session, one quick announcement. We finally managed to put correct videos to the conference website. You got the link by email if you are a participant, but if you're not, you can just go to the website of the conference and there is the red rectangle which you need to click, and that will take you to the recordings of the past sessions of the 2 days. Today's session on the red novae and transients is longer than all the other sessions. We have 6 talks that you can see here in the program. So probably we'll go a little bit over time, but especially if we have a lot of topics to discuss. And just to have everyone on the same page, I prepared a short introduction to the topic of red novae. And the stories really started in 2002 when VLTI erupted and showed very peculiar characteristics that was unusual for classical novae, and people quickly realized it was something completely different. VLTI and many other red novae outbursts at high luminosities. For VLTI Monocerotis, it was 10⁶ solar luminosities. And during the event, they blow to very high extent, to hundreds of to radii of hundreds of solar radii. But maybe most characteristically, the temperatures after the outburst dropped to very low values. For VLTI Monocerotis, it was something of about 2000 kelvins. In this phase, they produce lots of dust. Sometimes this dust causes extinction, so they become red. So they red because of the extinction and also the low temperatures. That's why red novae. There is many different names. People come up with different categories within this small group even, but I think it's futile to discuss the names now. Let's move on. In our galaxy, we think we identified 4 or 5 objects of this type. The oldest one is a remnant of CK vulpecula, which was observed by Hevelius in 1670. But of course, as you probably all are aware, there is over a dozen of similar objects that have been identified in the local group of galaxies. So they all share the same characteristics, and it was shown by Noam, Soker, and Romuald Tulenda and others that the best interpretation of those eruptions is that they are manifestations of ongoing stellar mergers. And the Rosetta Stone object of this group is, of course, V1309 Scorpii, which we were lucky enough to observe many years before its eruption as a red nova. Those green points show the variability, and what looks like a noise, the few thousand days before the eruption, is actually physical variability. Because the object back then was an eclipsing contact binary, which we know now had a mass of about 0.2 and 1.5 solar masses after going through rather complicated evolution. To read about this, go to Kazimierz Stępień paper. So why we talk about this object here? It's because after shortening its period, it entered the common envelope phase. You can see that the variability, the binary variability that we observed for many years, disappears sometime just before the eruption. And the common envelope phase was very short. It lasted only a few weeks, or maybe months. So this is the connection to our conference, that those merger events are probably the most catastrophic form of common envelope interaction. And of course, we know more and more of those objects, so they become more relevant because their luminosities are between those of classical novae and supernovae. We can observe them in nearby galaxies. And we'll go back to that later. So the question I would like to ask here is whether we can learn something about physics of common envelope interaction or binary interaction by from observations of red novae. And you can attack this question from different angles. I think it's relevant to ask whether we can learn something about progenitors about observing the eruptions themselves and studying their remnants. So when it goes to progenitors, there is only a few objects for which we have any information about the progenitors. But probably the most relevant information we got so far is that there might have been some pre-merger mass loss through the outer Lagrange point, like it is predicted by many simulations. Eruptions also provide a lot of information, especially about the population of those merging systems. But I am most interested in the remnants that can be observed tens or hundreds of years after the eruption. And from those, we can definitely learn something about the structure of the remnant. Here is, for instance, a reconstruction of the remnant of CK vulpecula, which is particularly complex. That's the object that was observed that we now study 300 years after its eruption. And there may be some fallback and active jet ejection happening even now. We don't really know, but clearly this remnant is bipolar with a lot of complexity. Another reconstruction we were able to make was for V4332 Sagittarii, which is a twin system to V1309 Scorpii. And in this reconstruction based on ALMA data, you can again see this bipolar structure. Whether it was formed by jets or some other physics is unknown, but this simple model that we were able to create based on ALMA fits very well to models like that one of Andrei Pejcha shown here, where the merger ejecta, which is more or less spherically symmetric, interacts with the material that was lost before the merger and accumulated mostly in the orbital plane. So then there is some deflection going on, and eventually you end up with this bipolar structure. But having multiple elements, multiple components in those remnants, it's very difficult to figure out what was the physics. When we look at the object, we don't know really which part of it comes from the merger ejecta, from pre-outburst mass loss, or some other related phenomena going on in between. And to study those objects in very detail, because they are very high distances, usually at kiloparsec scale, we need to use interferometers, the technique that is most challenging and difficult. But for instance, to investigate the disks that can be related to those bipolar structures, we need the highest resolution possible. So usually in this epoch, we need VLTI interferometer and other optical interferometers. We have learned some interesting facts about red novae remnants. For instance, we constrain their masses. Usually we get masses that are of about a few percent of the mass of the progenitor for the circumstellar material, of course. We can measure the kinetic energies that are stored in the remnants, and also linear angular momentum. And both energies and the angular momentum are very similar to outflows of some of the preplanetary nebulae, which have been studied in the past, like, for instance, by Javier and Valentin Bukharaval. So you can, maybe this coincidence, maybe this similarity is coincidental, but you can speculate that maybe some of the preplanetary nebulae or objects that we classify as preplanetary nebulae are actually merger remnants. Or you can go the other way and claim that the mechanisms that form those different nebulae are similar, and this is why the numbers match. What can we learn about stellar mergers and common envelope physics from observations of the more distant objects that we see only during the eruption? Here you have a list, probably, which is still incomplete, of objects that are classified as red novae, luminous red novae, or similar objects. And you can see that they are at distances of megaparsecs or tens of megaparsecs. So we mostly see them during the eruption, and the zoo of light curves is quite impressive. And although there have been some attempts to explain those different light curves, I think we're still far from understanding them. And maybe this is one of the points we can discuss after the session. Also, from observations of those galactic and extragalactic objects, we learned something about the population of merging systems. Here you can see a figure from Nadia's paper, where you can see that the masses of progenitors go from below 1 solar mass up to 60 solar masses. So we are dealing here with low mass stars and high mass stars. And also for those cases when we know something about the progenitors, it seems that we have different, we're dealing with different evolutionary stages. So we have main sequence and pre-main sequence stars, like in the case of V3 monocerotics. We have those interesting subgiants, like famously V1309 Scorpii. We know about some massive subgiants or supergiants. That's one of the talks that we're going here today about 2018 BWO. Probably we also see remnants of mergers in red giant branch stars, maybe CK Vulpecula or BLG 360. And there were some claims that NGC 300 OT was related to an AGB or a super AGB star. So we have many different evolutionary stages, and the topics of our conference this week cover many of those phases, maybe except the pre-stellar phase, the pre-main sequence phase. There is not much work I see being done on the early stages of stellar evolution, but I think it's very relevant for the topic. There was this famous explosion in Orion molecular cloud 1, where you have those multiple stars running away from one point, and this more or less spherically symmetric ejection of the so-called fingers, so collimated outflows in different directions that we would like to understand, and we would like to know whether they are related to those mergers that we know from red novae. Going back to the populations, we know that at least one of those objects was a triple system. If you count this object into mergers, we're probably dealing with a multiple system interaction. So there is a lot of scenarios that produce red novae, and I am happy to hear that many of the theoreticians try to attack those different scenarios and try to explain the physics that is behind the observations. So without further ado, let's go to our first talk of the series. Zain, are you ready?
Yes.
Please share your slides. So Muhammad Zain Mobin is the first year PhD student at Nicolaus Copernicus Astronomical Center. Now we can see your slides.
All right, yeah. So I'll just go ahead and start. Thanks, Tomek, for the introduction. Today I'll be talking about recent results regarding the stellar merger remnant VA3 at MON. So VA3 at MON underwent a red nova event back in 2002, where it reached a peak brightness of over 1 million solar luminosities. Later on, after the outburst, it cooled and its spectral type was found to be an L type. Later spectroscopic observations showed molecular lines in the circumstellar environment, and dust formation was also found to be occurring. Regarding the mechanism behind the eruption, it's thought to be a stellar merger of a pre-main sequence star and a main sequence B-type star. The mass of the pre-main sequence star is thought to be 0.3 solar masses, and the mass of the B-type star is thought to be 8 solar masses. It was also discovered later on that VA3 MON is essentially in a binary system, and it has a B-type companion. So the merger occurred within a triple system. So later on, because of the dust formation, the B3 5-star was eclipsed. Its spectral features were no longer visible, and because of that, by timing the eclipse, the distance was determined, which turned out to be 250 AU. In a interferometric study, the first one in 2005, the diameter of the central merger remnant was measured, and that turned out to be about 8 AU. So studies, the study of the spectra with the sub-millimeter array revealed CO and SIO emission features. And also, another interferometric study in 2014 revealed the presence of this stretched elongated structure around the central merger remnant. All right, so for one of our studies, we used the ALMA array. We used it in the extended configuration, which enabled us to have very high resolutions of up to 20 milliarc seconds. And these observations were carried out about 20 years after the eruption. So what does the ALMA data reveal in the millimeter? As you can see on the left, we have this very complicated structure. It has distinctly, it's divided into three components. We call the central component where the merger remnant is located. We call that component M. Component B is the position of the B-type star and the stuff encircling it. And finally, there's this extended clump of dust that's a bit further off from the main system, which is just, we call it the clump. This is also the first time that the companion is directly observed. And so the position of the companion is directly observed. And so we have a revised distance of 230 AU. The spectral features show the presence of simple metal oxides with line velocities of up to 300 kilometers per second. What's interesting is that the features, there tends to be some differences in the molecular emission, and that's most noticeable when we compare the CO emission with the SIO emission. So on the left, you see the channel maps for CO that map the emission around the merger remnant. On the right, you see the same thing for SIO. And if you look at some of these carefully, you'll see this chunk missing out in the SIO, which shows that there's the northwestern region has this area of depletion for SIO, whereas in the case of CO, it just seems like it's enhanced in that region. So that's an interesting feature that we think has to do with shocks in the circumstellar material. Furthermore, if you look at the speed of the material around the merger remnant, and if you look at specific, pretty much the main molecular species that we were observing, it seems that towards the northwest, you have a lot more faster moving material. So it's a lot more redshifted. And that we think has to do with interactions between the material, the molecular ejecta with the B-type B companion. So it's probably accelerating it and causing it to do something that's that shows this asymmetry in the velocities. We also did model the SED in the dust emission. And the way this was done is for the central, the M component, a disc-like structure or a torus-like structure was used to produce the SED. And for the B-type star, we had essentially a spherical shell. And then finally, for the extend component, there is this 3D Gaussian. And what encircles all of this is another giant shell that we call the spherical ejecta. I'm just going to play this movie. Hope it works. So what's interesting is the nature of the material around the B-type star. Is it because if you have a B-type star, you expect it to photoionize its surroundings, but nonetheless we have what seems to be this stable cloud of dust around it, and furthermore, the extended cloud is also another interesting source of speculation. What created it? We think it might have to do with interactions of the B star with the surrounding material. So it might be deflecting it at some angle, which is causing the dust to sort of accumulate here further away. Another important thing to remember is that the M component, we basically found it to be this flattened structure with a position angle of -50 degrees. However, at the scale of component M, we're really reaching the limits of the resolution with ALMA. In fact, we're slightly below it. So that's where the VLTI comes into play. So we used the Matisse instrument, which is a 4-telescope combiner. We used the smaller auxiliary telescopes. The measurements were observations were taken in the L band, which spans from about 3 to 4 micrometers. What Matisse does is that it records the interference, the fringe pattern. And using this fringe pattern, we can extract interferometric observables that we then modeled. And namely, these are the two main ones are squared visibilities and closure phases. So in a nutshell, squared visibilities tell us about the shape of the source. And closure phases give us some insight as to the symmetry of the source, whether or not it's centrosymmetric or not. So we model these visibilities in 3 broad ways. The first being use just an extended component, a disk or a Gaussian. The second was an extended component plus a point source, the point source representing the central star in the merger remnant. And finally, we used an extended plus 2-point source modeling approach. And so if you recall, there's a VLTI at MON is in a binary system. And so we were interested in seeing whether or not the B-type companion shows up in the L band in the mid-IR. So what we found was that the separations of the point sources are actually much smaller than the actual separation between VLTI, the central star, and the B-type companion. Which leads us to the result that the B-type companion is not in fact seen at the L band, which is something that makes sense because you have a B-type star. You don't expect it to emit much in the mid-IR, especially near 3 microns. We found that the intensity profile for our extended component could be uniform or Gaussian. Both provide adequate fits. The important result is that the position angle for an elliptical disk is about minus 40 degrees. And so if you recall, for the M component, the modeling the SCB yielded a position angle of minus 50. So that tends to suggest that the orientations of the structure in the millimeter regime and in the mid-IR tend to match, and the flattening ratio was about 1.5. Here's just a model image for the elliptical disk. Although we did not have sufficient data, so we only had a single configuration, which is usually not sufficient for imaging, but nonetheless, we thought, well, let's see what it looks like. And so by using an image reconstruction algorithm, this is the image that we got. And so it's more to remember that this algorithm doesn't assume a model beforehand, so it's model independent. And so it's interesting to see that the structure that it's giving us is very similar to what we get from our geometrical modeling, and also what was suggested by modeling the millimeter SCD. This is something that we hope to improve on once we have further observations using VLTI. This material is essentially the warm dust that's close to the merger remnant. And what's interesting is that, as I mentioned before, dust-like structure was also seen back in 2014. So that means that we have this fairly stable disk-like feature that's persisted for almost a decade. So it's not a transient, and it's probably where the remaining angular momentum post-merger is stored at. So finally, just to put everything into perspective, this is a cartoon of what the interferometric measurements from 2012 to 20 suggest. So you have basically this giant elliptical structure, and the various instruments are probing different wavelength regimes, and they all seem to be aligned fairly well. There's some uncertainty on earlier measurements, but hopefully with future measurements, with future observations, we'll be able to sort that out. And yeah, that's my talk. Thank you for listening.
Thank you, Zai. Everyone is welcome to ask questions. And I see a raised hand already. No, not yet. But on the Zoom chat, we got a question from Fabian. And that's actually a question to me. How similar or dissimilar is eta car to the class of luminous red novae? So this question has been addressed by many studies now. From the observational or phenomenological point of view, I think the most interesting is that when people extracted the spectrum of the great eruption from the light echo that was found in a nearby region, they found that the eruption was rather cool. So they found a spectrum of K-type, which was rather surprising. So it was also very characterized by low temperatures. Now we're discovering molecules in the surrounding of eta car, which otherwise would be difficult to explain because of the harsh radiation of the massive star. And many people also try to explain the great eruption by a three-body merger, a very massive merger. And I know this question especially is important for Noam. Noam, would you like to comment on eta car question?
Yeah, I think it is similar. I don't think the triple star model will solve everything. Actually, it's a problematic because after the great eruption in 1837, in 1890 to 1895, there was a second eruption, which you cannot explain with another third star. So this is a problematic. We don't see any evidence for this. There was also previous eruption a few hundred years earlier, the Nathan Smith group talked about. So I don't think we need the triple. My view, and if you look at your very nice paper, Tomek, of the novae of 16 something, CK Wool, you see actually an S shape. So an S shape tells me there's a jet precession. So it cannot be collimation of a disk, a collimation of fast wind by a disk, because this will not give you nice S shape. So I think both Eta Carina and many of the ilots, I call them intermediate luminosity, optical transient, or luminous red nova, they have many, many names. And so I think they are powered by accretion and jets and sometimes merger. You have jets and then merger, or the opposite. So I think, yes, Eta Carina is similar. And in the site that I sent the link to, we actually group together Eta Carina and some of these erupting systems that are the subject of this session. And we speculate on some planetary nebulae that might have been such event in the past.
Thank you, Noam. Next is Javier Alcolia. Javier, can you ask your question on Zoom? Javier, can you hear me?
You're muted, Javier.
Oh, yeah. Sorry for that. First of all, thanks for the talk. I have a question and a comment. The question is, do you have an idea of the spectral index for the continuum you observe with ALMA?
I'm gonna answer this question.
Yeah, not off the top of my head.
No, the signal to noise for the continuum and the band coverage is too small. We had some SMA observations before in a broader band, but they were not sensitive enough to even detect the continuum. So indeed, we don't know whether there is a single spectral index for entire remnant or there is some difference. We try to get VLA observations to see the cloud, but we are not sensitive enough to detect it. So the spectral index has not been measured yet.
But then you don't know what is the origin of this further out component?
Well, the simplest is to assume it's just dust that is there in some relation to the presence of the B companion. So the merger ejecta was passing by the B-type companion, something happened and we have an overdensity, but that hypothesis has several problems too.
then the comment is that if you have a look at our paper on area query, what you see is that the effect of the companion is accumulating material at the other side of the companion. So that will make sense.
All right, great.
The point is that you don't see SIO where you see this dusty clump, which apparently is contradictory. But but having these streams of material going further out than the orbit of the companion is, I mean, you can reproduce that pretty straightforward when you have the binary, and the binary is, you know, pulling the primary and dragging the mass loss from the primary. I mean, it's not an easy, but that's one result you will always get, that having material at the other side of the companion.
Interesting. Great. Yeah, we'll definitely have a look at this.
In fact, you can have two spiral shapes, a double spiral. One is starting on the companion, and the other is starting on the opposite side of the companion.
Well, the only difference here is that the merger ejecta speed is a few hundred kilometers per second, 200 kilometers per second, whereas you're dealing with a wind that is 20, 30.
When the wind is too fast, then you only see one side spirals, and the drag of the material is much more difficult. But maybe somebody can do this simulation, and you can test whether it makes sense for your speed or not.
Yeah. Okay.
That's it.
Thank you, Javier. Next is Orsola.
So what's the series of events that triggers a merger between a main sequence star that's not changing much in size and a pre-main sequence star that, if anything, should be contracting? So what is the destabilization and then the bang of the merger? So
there is no firm answer to this question, of course. I think the papers by Tulenda and Noam previously considered the scenario relating to the fact that we treat monocerotis in a sparse cluster. So you have a dense field, and this has been always suspected to cause mergers or some interactions. Also take into account that if you deal with a pre-main sequence star, it still may have a disk. And that also has been studied extensively, that if you have a disk in a system, you may end up with some extra interaction. And thirdly, we're dealing here with a triple system. We don't know well the orbit of the companion. It's as you saw, the projected distance is 250 astronomical units. If you assume circular orbit in the plane of the sky, you get a period of 1,000 years. But maybe it gets closer to the stars. That's three options I can propose, but none of them is really firm. All right, do we have more questions? So I see Laura has a question on Zoom and on Slack, but I would like, if Laura you can hold it for the end of this block of talks, then we can discuss this after the next two talks, please. So thank you, Zain. Let's move on to the next talk by Andrei Pejpa.
Hey, hello, hi everybody. Hope you can see the slides and
yeah, we can see
me talking. Okay, great. So today I'll be talking about results from a recent paper that was led by Nadia Blagorodnyova and Jakub Klensky, and these two did most of the work, but are unable to present this research here. So I will do my best to interpret it for you, even though I saw Nadia around. So maybe she can answer some of the questions in the end. Our work is about one particular luminous red nova, but I will give a brief overview of what we think these objects are, or what do we observe. Here is a summary of light curves of some of these events from a recent work by Andrea Pastorello. And we see that these events have sort of three distinct phases. First, some of these events show a distinct slow rise to the maximum for hundreds of days or several years, The most prominent of these are V1309 SCO and M31 Luminous Red Nova 2015. Then during the main part of the event, there are often two peaks. One is relatively short and the second is longer, often resembling a plateau, similarly to type 2 plateau supernovae. And final phase is a dust formation, which occurs typically a few hundred days after the main peak. So we have three phases of these events that have been investigated separately. So for example, for the slow rise, we have argued that these are caused by internal shocks in a material that is gradually leaving the binary. The mass ejection is a dynamical event that has been investigated many times in the field that would correspond to the common envelope or stellar merger, the dynamical phase. And we have seen contributions on this during this conference. The optical emission of the transient has been argued to be caused either by diffusion of light through recombining hydrogen shell, potentially with some aid of recombination energy, or we have argued that this is caused by shocks between two components of the ejecta, which can potentially give more EV per baryon than recombination. However, these three stages are connected together, and what we aim to do in our paper with Nadia and Jakub was to investigate these connections and provide a uniform or connected picture that covers everything from before the observations to the peak of the transient. In order to do this, we had to model the progenitor, calculate binary star evolution, that explains how the system got into the current or into the unstable phase. And then what we could do was to use the common envelope ejection formalism on a realistic primary that actually matches the observation of the progenitor that we have. That would explain the mass ejection. And then we can confront this in the final step with a modeling of the transient and put the entire picture together. So why this transient? 2018 BWO in NGC 45. The big advantage of this transient is that it has HST images about 14 years before the outburst in 3 bands, which allowed us to determine the temperature and luminosity of the progenitor. We can show it in a Hertzsprung-Russell diagram, such as is shown here. And what is typically done in these cases is to interpret this position with single star evolution tracks, as is shown here. If we do this, we would find out that the progenitor was likely an 11 solar mass star or so. However, we know, or we think, that luminous red novae are associated with binary stars. So we need to have binary star evolution models to explain these observations. That's shown here on the right. And it shows Jakub's binary evolution tracks. They initially resemble single stars, but when the mass transfer starts, all of these tracks turn down quite rapidly. And this is a typical signature of a thermal timescale mass transfer or mass loss from the primary, where internal energy and luminosity on the core is used for restructuring of the star instead of being radiated from the surface. So one conclusion from this is that the masses of the primary that we get from this are higher than from the single star evolution, but we can do many more things. So what we can do is that we can look in detail on the mass loss history from the primary star. This is shown on the diagram here on the left, which shows time in hundreds of years or in years. And remember, the orbital period of the binary is about 1 year. So this is truly hundreds of orbits. And this shows the mass loss rate from the primary. Here is an equivalent plot, which shows the mass loss rate from the primary, which is monotonously increasing in time. And this is the relative decrease in luminosity due to restructuring of the star. And the black dots in all cases indicate the position that matches what we observed for the progenitor of this event. What we can conclude from this is that this object was undergoing sort of a semi-stable mass transfer on thermal timescale, reaching very high mass loss rates, 10 to minus 3, 10 to minus 2, or potentially 10 to minus 1 solar masses per year. And what is also important is that the primary during this process lost a few solar masses, so tens of % of its mass. And most of this mass loss did not land on the companion, but quite likely was ejected into the surroundings of the binary, probably somewhere around the L2 point. Now, we can take this one step further, and we know what the structure of the primary star looked at the moment or about 10 years before the dynamical event. What we can do is that we can apply the common envelope formalism to the structure of this star to see what we find out. This is shown here on the left on this panel, which shows the mass coordinate of the star measured from the surface. So center is to the left, and this is energy. The black line is the binding energy as a function of mass coordinate, taking into account the kinetic energy of the ejecta that we observe. The colored lines correspond to energy that would be deposited by a companion of a given mass if it spiraled to a given mass coordinate. And when these lines intersect, we get predictions for the amount of mass that was ejected during this event. And you can see that for reasonable companion masses, we predict mass ejections of a few tens of solar masses. In all cases, the companion mass is too low to have a successful complete ejection of the envelope. So this was a stellar merger. Another interesting insight into this issue can be obtained by looking at a mass from the surface as a function of radial coordinate, which is shown with the purple line. So for example, if we wanted to unbind one solar mass of material from the surface, we would have to go all the way to about 30 solar radii right here. The yellow line corresponds to a local escape velocity as a function of the radial coordinate inside the star. And this is useful because during mass ejection, we would expect that the asymptotic velocity would be approximately similar to the escape velocity at the radius where most of the energy deposition occurred. So based on this, we would predict that the asymptotic velocity would be a few hundred kilometers per second. So now we can go to the properties of the transient, and we can model or describe the observations to obtain ejecta velocity and duration and luminosity of the plateau. So we have these three observed quantities, and we can invert the analytic relations that we have in the two models to get some properties. And first, the two-component shock power model, we get masses of the two components. Mass of the wind, in this case, is understood as the mass that is gradually left or lost from the binary before the dynamical event occurs. And we find two solar masses, which is roughly compatible with binary evolution. Mass of the ejecta is the dynamical component that goes out faster and collides with the pre-existing distribution. And we find that it's few tens of solar masses, again, in agreement with the common envelope formalism. The second option is to use a scaled-down version of a type 2 plateau supernova modeling or analytic scaling relations. And there have been a number of these in the literature, which differ by the numerical prefactors in the analytic scalings, or sometimes in some of the power laws, in the exponents of the power laws. And what we find is that the results here differ quite dramatically among different prescriptions. The reason for this is that this inversion is nearly degenerate. The ejecta mass, that's one of the parameters, and the ejection radius are quite strongly degenerate, and the details matter. So that's why we got such a wide dispersion of numbers. But for the most realistic ones, like Suchbold and Popov relations, we get ejecta masses that are few tenths or maybe up to 1 or 2 solar masses, and the ejection radius, which lies approximately inside the primary star. So both of these possibilities can explain the observations given the limits of the models. So I would like to show a summary slide that explains what we think happens in these events. So first, there is a gradual loss of mass from the binary, which we can sometimes see as a slow rise in the luminosity. That's illustrated on this movie on the left. And then at some point, the binary goes dynamical and the 2 stars actually merge. So this is quite likely towards the end of the gradual rise. And as a result, the 2 components that we have there, the fast and slow, interact in a radiative shock, and we get the 2 components of emission in the light curve. And finally, this radiatively cooled shock region is dense and cold, and we can get dust formation in the shock shell. And I would like to conclude with a final slide. And that's that from this discussion, my understanding is that we need to work better on the modeling of the transients. And we have been trying to improve this situation in the past few years, thanks to Diego Calderon, who was a postdoc working with me. So what Diego did was that he implemented a gray flux limited diffusion with implicit time step in a 2D hydrocode with an expanding mesh that is extremely well suited to modeling of various transients. So what you see here on the bottom is a movie of a spherical explosion colliding with a circumstellar disk. And notice the vastly different and changing range of spatial and temporal scales. So we plan to apply this to luminous red novae. So stay tuned. Thanks for your attention.
Thank you very much, Andrzej. Do we have questions to Andrzej? Please, Adam Frank is raising hand. Please go first.
Yeah, just the question actually about the disk, right? So you're going to get a lot of shaping in that environment beforehand, and including the possibility of a disk around the secondary. So it wasn't clear to me how much that plays a role in the. I mean, so that movie, it sounds like that movie you just showed was for something else, but
Yeah.
You anticipate that the geometry of the material, of the circumstellar material, what role that's going to play?
Yeah, so what you are asking for is related to this movie, which is small, but I hope you can see it. So the binary in this case is not modeled. We inject material close to L2 and follow what happens to it. And it can either leave to infinity or build up a circumbinary disk. Right. But in all cases, it's kind of concentrated in the equatorial plane. And then probably the subsequent dynamical event might not be completely isotropic, but it's quite likely more spherical than what we've been getting before here. And these 2 components collide, and we get a transient.
Yeah, well, it's interesting because on your top image there, you're showing the spiral shape, and of course, we know that we see those spirals in relatively spherical AGB winds when we've got binary. So where you have a spiral shape, but you still have a spherical wind. In this case, I guess you don't expect to have such a strong pre-existing spherical stellar wind. The mass loss rates are not high enough for that really to matter. So
yeah,
really
yes, this spiral shape, actually one can get similar spiral shapes in different contexts. So you mentioned one which is caused by gravitational focusing due to companion. One gets similar things in Wolf-Rayet binaries, for example, but here it's for a different reason. So the stream goes out and it expands adiabatically, and then it collides with itself. So it's essentially the shocks here correspond to sort of homogenization of radial velocity in the stream. And of course, the time-changing tidal field of the binary plays a role. I mean, it spreads the stream kind of in the orbital plane. It differentially torques it. but it's a little bit distinct from the gravitational focusing that you have in mind.
Right, right. And so there's very little material above and below the plane here.
Yes, I mean we assume zero,
Okay.
basically. It's the width or the scale height of the disk is basically proportional to the ratio of like shoe and Lubov kind of thing, the temperature of the mass when it's ejected relative to orbital speed, which in most cases is much smaller than 1.
Right, right. Thank you.
Okay. I see Alexei is raising his hand.
Yeah, thank you. I was curious to ask, so like if you look at observed luminous red novae, can we get spectroscopic information about the velocity of material? So like what sort of velocities we expect in the observed events and what sort of velocities we expect if the events are produced in a disk-like configuration? Are they consistent?
Sorry, could you repeat it perhaps slower? I didn't understand well.
Yeah, sorry. So I mean, like if we observe a luminous red nova, an observed event, transient, then we can take a spectrum, and from spectral lines we can infer the velocities of expansion of material. So that's going to be velocity number 1. Then if we take a model of disk-like event wherein the shocks are produced in a transient, then we expect some other velocities or some similar maybe velocities, velocity number 2. So my question is twofold. Firstly, do we have constraints on observed velocities? And secondly, if we do they agree with the disk-like origin?
Okay, so I will say a couple of things about this. So we expect that the velocity of the material is similar to the escape velocity at the location from which it was ejected. So this velocity of this stuff that is shown on this movie, like this pre-existing disk, is a fraction of the orbital velocity of the binary, maybe 20 or 30%. Mm-hmm. But then the binary merges and the physical scale becomes much smaller. The companion plunges in and the velocity will be faster. So and as a result, you have later ejection of faster stuff and a previous ejection of slower stuff. These two components collide, mm-hmm. and there is a velocity difference. So in the theoretical model to explain the light curve, this is just parameterized by a factor. We assume that the previous ejection is a factor of 4 or 5 slower than the faster one. But this actually matters quite little. From the point of view of the moving material, the pre-existing stuff is basically stationary because the kinetic energy is velocity squared. So does this answer your question?
Yes, so I understand the velocities are comparable. The only thing is that I wonder is about radial velocities, because we kind of look and the velocity we measure spectroscopically are in our direction. So like we have to have velocity of material in our direction comparable to the orbital velocities.
Yes, so maybe Nadia could explain this more, but typically in transients people look at the full width at half maximum of spectral lines and associate this with some kind of a typical expansion velocity, because we see stuff that is coming toward us, but we also see stuff that is going sideways, so we have some kind of velocity difference. We probably don't see the stuff that's going further away. If there is a p-signy profile, then the radial velocity of the absorption trough is a better indicator of the expansion velocity.
Well, if I can say something, basically we need a higher resolution than what we are currently using for observations of luminous red novae to actually distinguish properly the profiles. I mean, we see that there is a low velocity absorption generally on top of the emission lines, which suggests that there is some material in front of us, which is actually absorbing. But yeah, we need better resolution to actually be able to say more about what exactly is happening there.
Nice, thank you.
Okay, thank you both, Alexei and Nadia. We still have a question from Elena. Hi, Elena.
Hi, my question is more trivial. In a sense, I'm looking, the model is done on light curve. And not all the gap transient or ILOT that have from the extragalactic observation have two such mark peak. Some have more a second plateau or something like that. And these turn them similar to other transients. So I wonder how secure is or how strong is the modeling of this phase and whether there are degeneracy or some limitation of this type of modeling for the fact that indeed it's based only on photometry and on spectroscopy.
Mm-hmm. Okay, so I will give two answers to this. So, in sort of a cartoon picture that is shown here, the shock interaction region can be engulfed by the faster ejecta. So essentially acts as an internal power source that sits inside the hydrogen-rich ejecta. And similar situation has been investigated in supernovae. For example, you take a hydrogen-rich supernova and then you put in inside a spinning down magnetar as an internal source. And there are also these type 2 plateau N supernovae that have been investigated by Nathan Smith, where the picture is similar to what we have here. So the plateau that exists there because of hydrogen recombination can be made brighter and longer by an internal power source, which could be a magnetar in case of supernovae, or embedded shocks in the case of supernovae and potentially stellar mergers. And how well can we model this? I would say we are just starting. So we have relatively simple analytic or semi-analytic models, but we are moving toward numerical simulations. So this movie shows density and radiation energy density of this setup. So in principle, we will be able to get light curves from different viewing angles for this setup, but we still need to do a bit of a work to adapt this to the context of luminous red novae, in terms of more realistic opacities and equation of state.
Okay, thank you. But can I be provocative at this point? I can imagine two other transients that has a light curve with plateau. And for what we know about them, they don't need magnetar, they don't need internal shock. One is U-Scorpio, classical nova, and the other is Sagittarii, a dwarf nova, which are totally different type of transient, but still they have a light curve with. In this case, it's missing the slow rise, but there is a peak and there is a plateau.
Yeah. Okay. Yeah, I admit that I don't know that much about classical novae, but I agree that more work needs to be done to identify the cause, and I mean perhaps more quantitative modeling of not just the plateau duration and luminosity, but also the shape, taken together with all other information.
Yeah, I think that the use of spectroscopy should be always included in whatever modeling, global modeling that is done as a bottom line.
All right. Thank you, Elena, for your question. I think, Adam, do you have a new question, or this is still the first one that I see?
No, that's sorry. I need to remove
Okay, no problem. All right, let's move on to the next talk now. Thank you, Andre. If you can kindly please stop sharing the screen. And I ask Zuo Chen to try to share his slides. Yes.
Hi, can you see my slide?
I can see your slide. I can hear you. I cannot see you, but I guess that's your choice.
Yeah. Oh, okay. I will turn on the video. Yeah. Thanks. So thank you. Thank the organizing committee to give me the opportunity to present my recent work with Natalia and Ivanova. So I'm going to talk about the gap transient. The gap is defined as in the in a magnitude versus decay time diagram, the gap is found between the classic nova and the supernova. The classic nova is located in the lower left part of this diagram, and supernova is in the upper part. Then the classic nova usually have total energy release of 10 to the 44 erg, and the supernova is 10 to the 51. For comparison, the radiation energy loss of V39 scale is roughly 3 times 10 to the 43 erg. And gap transients, please allow me to call that for short because they have various names, but gap transients show a broad band of H alpha emission that on the right panel. And that means it implies that the gap transients usually have expanding envelope. And the left panel is just the inverse of the magnitude versus decay time. And the full width, the breadth of the H alpha is usually hundreds to more, at most 1,000 kilometers per second. And recently, luminous red nova is recorded by the ZTF called AT2019 ZHD, showing in the green stars, and together with many other previously documented gap transients, including the famous V39 skull. And we can see that the AT2019 ZHD is the light curve is similar to the V39 skull, but roughly 100 times more luminous. And it is well documented in the sense that we have a broadband light curve of it. And the author hypothesized, and we think it is true, that the H alpha, the hydrogen recombination contribute to the plateau of the light curve. And because given this information, we model our one-dimensional radiation hydrodynamic model as an expanding shell or ejector. It is expanding so as it cools, and the hydrogen inside it is recombining. And the right panel shows the Rosland mean opacity. When the ejector is in high temperature, it is fully ionized. So the opacity is high and it is opaque, thus opaque. As it expands, the density drop and the temperature drop, then the opacity come to the wide gap inside, and it become transparent suddenly. And after a short time, when it comes to the dissociation and dust formation region, the Rosland mean opacity become high again, and it becomes opaque again. So in the overall behavior in the light curve will be like in the end, towards the end of the transient will be like transparent and then opaque again because of dust. So we set up our one-dimensional model as we model the hydrogen and the helium, and we set the hydrogen mass ratio to be 74%, and we consider the hydrogen ionization and the dissociation. And we also consider realistic gray dust and gas opacities. We use flux limited diffusion approximation, and we use adaptive mesh and static mesh refinement to improve our computational efficiency. The inner boundary is set as an outflow spanning a period of time, and the hydrogen in the outflow is fully ionized at the temperature of 25,000 K, and the radiation gradient is 0. So there's no radiation flow at the inner boundary, but the outer boundary is fully transmissive. The initial condition is of the density is a power law density profile with a floor density of this, and we set the initial temperature as cold. The central mass is 1.6 solar mass, 1.6 solar mass object to mimic the V39 scope. So on the left panel is our result with the eject speed of 1.1 escape velocity. And we can see that the temperature drop and the radius of the photosphere expand, and the luminosity has a plateau. The plateau is, I don't have a pointer here, but the plateau, I mean, is the first rise up of the plateau. Okay, the second plateau is actually the recombination from atomic state to the molecular state. So on the right panel, we see the result with 2.5 escape velocity, and the difference is that the peak is ahead of the slower ejector. So the left panel and right panel all have the same amount of mass and energy. The energy is listed as the internal energy, not the total energy. The kinetic energy is one order of magnitude larger than the energy number. Yeah. So there are three stages in this event. One is the expanding stage, expanding phase. So in this phase, the ejector is fully ionized. On the left panel, we showed that the luminosity, density, temperature, and fraction of hydrogen of different species. So the black line is of the fourth panel is the ionized shows the ionized hydrogen. So we see that the inside of the ejector is fully ionized, but the outside is molecular, shown by the blue line. And in the second panel, to be careful is that the double y-axis, the secondary y-axis shows the mean free path over the radius. And when this number is greater than 1, that means the mean free path is bigger than the size of the object, then it's in the optically thin region. But when it's smaller, much smaller than 1, it's in an optically thick region. So the y-axis, the secondary y-axis, we see that the red line is below 1 inside the ejector, but on the outside it is bigger. And the second phase is the peak of the luminosity. And at this phase, the inside is still ionized, but outside is molecular and atomic, all atomic. And the ejector is very thick, but we can see that the mean free path over R, it changes from 0 from 1 to 10 inside this ejector, thick ejector. As you can see, the density profile here is high. And the last phase is H2 recombination. So the inside ejector has now become atomic, and the outside is molecular, and the hydrogen, molecular hydrogen, form on dust. And yeah, you might wonder, sorry, my computer just stuck. You might wonder what will happen if we, what will happen if we eject the first fast one first, then followed by a slow one. So the right panel shows the light curve of this event. We apologize that we don't have time to run high resolution simulation of the red and the blue line, but the blue line shows high resolution one, but the green and the yellow one, we don't have that much high resolution, so it has some numerical error. But we can improve the resolution later. the left panel shows the simulation of the right, the blue line. And we see that as the first shell expands faster, the second shell cannot catch up, and the luminosity first rise rapidly and then suddenly become transparent, and the opacity just become very small, and the object become transparent and the luminosity decrease. And then as it reaches the second plateau is the hydrogen molecular recombination, and then it comes to the second plateau because of the latent heat by the recombination energy. And at last is just the atom become fully molecular. And thank you. This is all of my talk. This result is rather preliminary, and we are going to write a paper about this later. Yeah.
Right. Thank you, Zuru. Questions to Zuru? Please raise your hand or use the different chats. So Zuru, when you considering dust formation, what is the dust formation criterion? Is it the density or temperature?
Temperature. So the dust usually form at 1300 K, and the opacity here we have is So you see the opacity. So that dust only play a role in the opacity here. Mm-hmm. So when the temperature just drop below 1500 K, we use dust opacity. Then it is used. Then its presence is presented. Yeah.
Right, but you assume some efficiency of dust production out of H2, right?
Yeah. But the density. Let me be clear. The density here in the ejector here is very high, 10 to the minus 11 gram per centimeter here. Mm-hmm. So when at this density, the dust can form very rapidly, very efficiently, and the molecular can just form on it also very quickly.
All right. I don't see any raised hands on the Zoom, but I see a question of Chris. Krzysztof, you would like to ask your question online?
Sorry. Let me answer your question in another way also. So actually, there is another channel for this high density, 10 to the minus 11 gram per centimeter cube. The hydrogen can form by its own, by three-body collision. That's three atomic hydrogen collide, and then they release one as hydrogen and another one as atomic hydrogen, one molecular and one, This is because at high density, the cross-section of the hydrogen, atomic hydrogen increase,
Mm-hmm. Well, I am concerned because the dust formation, our understanding of dust formation mainly comes from AGB which are slow and maybe slightly different than what we're dealing here at higher velocities. So that's why I'm wondering what theoreticians use. But thank you for your answer. Chris, are you still there? Would you like to ask your question?
Yes. Sorry, I'm on another conference right now online, so I will just join with Mike. Zu, good talk, but I have a question. Model setup. Yeah. I understood most of it, but could you tell us what are the shortcomings? What are the problems? Could you improve on something in near future?
In the future, I think I don't know. I think I have a code.
What is the weakest? Okay, let me put it that way. What is the weakest point of the current setup?
Oh, of current setup.
Yes, the one that you presented.
Yeah.
The weakest point.
So you see, some gas can fall back.
Okay.
Some gas can fall back. However, in a 2D or 3D setup, the angular momentum will reduce the fallback. But anyway, some will fall back, and the fallback will come to the surface of the merged binary and form a shock. This shock can be also very luminous and illuminate the ejecta.
Okay.
Currently, I don't model this fallback and the fallback shock. Yeah.
Okay, thank you.
Yeah, thanks.
Well, thank you both. I see.
Also,
Yes.
I would say that there are many parameters that I cannot explore them one by one now, because, for example, the initial temperature, actually the more precise measurement should be the initial entropy, which is usually roughly the initial entropy of the giant star. But here, I just pick a number, and as I tested this, at this temperature is usually the similar entropy as the gas inside the giant star. Yeah.
Thank you. Roger, would you like to ask your question?
Hi, Joe. Good to
Hi,
see
Roger.
you again. Sorry, my webcam isn't working, but I was curious if you included considerations of formation of ice and grains in your dust, and if not, how do you expect that to change your results?
The opacity table has included the formation of like different. It has 5 kinds of dust, including water, methane, and silicate, and such as 5 kinds. So I'm only showing the temperature here to be 1000 because the relevant temperature in my regime is roughly a few hundred. You would not expect like ice methane to form, or water also will become vapor or just gas state.
Thank you.
Yeah, thanks.
Oh, thanks, Roger. So I think now we can get back to the question of Laura. Laura, are you still online? Would you like to ask the denial question and the follow-up discussion that took place on the Zoom window and on Slack?
So
Sure.
I will stop sharing, right?
Yeah. All right. Thank you. So,
stop.
I suppose it's primarily a question about nomenclature.
Mm-hmm.
I was curious why folks often call luminous red novae stellar mergers.
Mm-hmm.
And in particular, I was curious how, in the case of V1309 SCO, which I think is the best observed luminous red nova, how we in fact know that is a merger, because it's been heavily obscured ever since the eruption. And so even though we have these beautiful observations of it pre-eruption, we don't know much about what actually happened to it post-eruption.
So did anyone answer your question conclusively, or you still have doubts?
Nadia answered it conclusively.
Okay.
So she pointed out that for the good observations we have of the progenitor, and also of the progenitor system, we know that if the envelope had been ejected, then the energetics of the system imply that it must have merged. Did I say that right? I think I said that right.
All right. So for V1309 Scorpio, we are very unlucky because it was an eclipsing binary. So we really see the system in the plane of the orbit. So whatever was lost in the plane of the orbit is going to be obscuring it. And indeed, recent observations show that it's still very obscured. Also, it's very difficult to observe this particular source because it's a very dense field, difficult to make spectroscopy and photometry of this guy. But shortly after the eruption, when the object faded, we should have, if there was still this binary there, we should have still seen the modulation in the light curve, in the later phases of the light curve, where the object was still bright, so we could see that, so we could see it. So I think there is a compelling evidence for V1309 Scorpio. I wouldn't say it's so for all the objects that we call red novae, but the nomenclature, as you said, is a pain. Everyone uses their own name, and it's very difficult sometimes to understand what people mean by that given name. Are there any comments to follow-up comments or questions to what Laura said?
Maybe could I just
Yes,
say, so
yeah.
one potential alternative would be to call it a common envelope event. The thought that like anytime a binary ends up in a single envelope, that would be a good.
Well, it may be more difficult to prove there was a common envelope phase than to prove there was a merger, I would say.
Yeah. So I don't know if there are other possibilities for names.
I don't know, Laura, my personal thinking is somewhat along the lines of yours in the sense that like, don't we know, Tomek, in that case or in general, that the two stellar cores were more compact than the envelope that surrounded them? And if we take the idea that like this umbrella of events, whatever we want to call them, have two possible outcomes, then that's at least one way to go about the nomenclature. But I wondered if we could talk a tiny bit more about, like, in general, how we might know what the outcome is, because I think Nadia's argument is a really strong one about the energetics and the amount of mass involved in the ejecta or remnant, and like asking whether that mass is similar to the envelope mass that would need to be ejected. But if there's a general strategy to distinguish these, I think that would be really transformative, that didn't rely on what we think will happen, because, you know, I think the real value of these observations is that they can challenge what we think we know. So I don't know if Tomek, you wanted to revisit that, or if Nadia did, or basically anyone who knows more than I do.
Making a step back to the terminology again. I mean, we have this phenomenological name of those events: red novae, luminous red novae, intermediate luminosity transient. So this is what we see. A merger thing is interpretation, and I think I would say people are careful in saying it. Sometimes they call it merger candidates and so on. So yeah, I think people are careful, but maybe if someone says us that we're not careful enough, maybe we should revisit that. About your comment, Morgan, so as a simple observer, I can only tell you what I see after those tens of years. And for the galactic objects, the situation is quite clear. It's true that many of them are obscured. The 38 Mon seems to be clearing out of the merger ejecta. We can now start to see the photosphere, clear photospheric lines from the merger product itself. The spectra we get for this object are very good quality. So if there was a binary which see a dance of spectral lines, we don't see that. It's a single object, complicated object. But nevertheless, it does look like a single star. Of course, you can always claim that the binary is hidden below the photosphere. And I don't know what to do about it other than wait and see. Maybe someone else would like to address Morgan's comment. I see a lot of raised hands. Maybe Stephen, you were first.
Thanks, Tomek. Yeah, Morgan, it's sort of in the same spirit as Foucault's The Naming of Things. We're getting a little nominalist here, and it really worries me that we're putting the cart before the horse by naming physically the scenario and interpreting the observations according to a particular scenario. I think we're frequently missing things. And I've been as guilty of this as anybody. Sorry, let me just mute for a moment because I'm near an airport. Okay, sorry. But Tomek, you said that in V1309 SCO, the system was an eclipsing system. If I remember right, it was an elliptical light curve. that we don't know the plane of the orbit. It was continuous. I don't remember that there was an eclipse, but the key thing.
Yeah, Andre had a detailed model of this.
Yeah,
I missed this part of it.
Well, I guess for contact binaries, the eclipse is not as well defined as for detached ones. So there is this degeneracy between inclination and mass ratio that all
because it's common envelope
amplitude.
So
yeah, well, but that's different common envelope than the common envelope we have.
Yeah, right.
About, which is extremely confusing to me.
It's a hydrostatic. But I'd also just mention an observation that was made, but we wound up never publishing it. About 10 years ago, we tried the system with Chandra under the thought that there might still be in the remnant some kind of an active dynamo and perhaps even coronal type emission in the X-ray. And zip, the optical depth in the environment is just too high. It's well above 10 to the 24 per square centimeter. And so there's no indication of there was no indication of X-ray emission. It might be an interesting thing to look at subsequently in X-ray, perhaps even with something like New Star, to see whether there's any indication in these remnants of enhanced dynamos. But that was my only comment, so thanks.
Thank you, Steve. Next is Adam.
Hold on. Yeah, again, I'm just going back to this issue. I raised this in the comments. It's not so much about nomenclature, but again, I'm just wondering, for me, it's confusing, having come to this field a little bit later in my life and, sort of having this model of common envelope in my head with all of its phases, the extended atmosphere, the eventual plunge in, now all we've learned from it, and this idea of mergers. And it's still not clear, and what we talk about when we talk about the luminous red variables, or luminous, the ones we're talking about, how I should model them differently in my head. Like, obviously, if you're having a merger, there's a brief period where everything is the same, and you could say, oh, there's a common envelope. But I mean, it seems to me like there could be very different sort of physics. And so here we are in a common envelope meeting, and we're, and we point to these objects all the time. It's like, oh my God, here are these great examples now that we've actually seen things that are common envelope. And yet it's still not clear to me how, when I think about quote unquote classic common envelope, how much of the physics is the same. So that's just a question for discussion.
Well, I guess V1309 Scorpio in this particular scenario gets a lot of attention because the amount of data we have. So we know this system very well. So if you want to eventually compare your models to observations, that would be the thing to go. Also, when you look at the statistics of those events and see that subgiants are the most likely ones to merge, then probably this also gives you a clue that subgiants are the best to study. Alexei, would you like to comment on that or some other topic?
On that, well, I mean, it's basically following again on the idea of merger or not or common envelope. The thing is that I would say probably we're talking about rapid mass ejection of some sort. It could be also stable mass transfer, also can happen over a short time scale of 100 years, 1,000 years. We eject mass and it's hot and it also produces some transient. And common envelope phases could also be between very different systems, as Tomek was describing in his intro slide. So it could be between AGP stars or massive stars, or between the low mass stars. It could be observed very differently. So I mean, we have some mass ejection, and I mean, we probably should have very different progenitor systems, very different physics at work. And the future probably is a bit in the direction of what we've heard from the talks by Andre, for example, or by Chen, namely in the same direction. So just making more advanced models of how mass is ejected and how radiation is propagating through that mass, and how we observe it as light curves, and what spectra do we get from that, and then maybe perhaps some models will match the predictions Just I think perhaps it would be more cautious to talk about it not as mergers but as mass ejections, and the future is probably about again making those detailed rotative transfer simulations.
Thank you, Alexei. Noam.
Yes, Adam, you asked if you can use the same model. In some processes you can, in other you cannot. If you have a compact companion enter, for example, to a main sequence envelope, take low mass main sequence star, it can enter the envelope of a more massive main sequence star because the lower mass star is more dense. So it gets inside, but don't use the alpha prescription because you don't have a core. So if with a main sequence star, you can spiral in and actually get less energy. So the alpha prescription will not work. But other processes like the initial spin up, if it acquits and launch jets, some of us like jets, it can work, but don't take it too far away as you are used to with RGB and AGB and super red giant stars. You don't have a core, the alpha prescription will fail. So the simple one, you can always adjust it. So yes.
Can I jump in right there just to respond to that? Because this seems like this is a paper being waiting to be written. Because we've all spent a lot of time over the last few years really delineating the processes from plungin or even pre-plungin, the stuff that Morgan and Ursula and others have done. Really trying to articulate there are these different phases of a common envelope, and we're trying to really articulate the energetics, the dynamics, what kind of friction is at work. And now these other objects, right, as Noam points out, there's no core, and there's much less star, right? I mean, there's literally orders of magnitude less envelope if it's a merger between two main sequence objects. So I think, it's kind of really would be worthwhile for us to sort of think about like how these systems are going to be different and how they're going to be the same. I like the point about in the end, there's ejection and you're going to get shocks through those ejections, probably because the energy released. So, maybe the only place they really are similar is the fact that you blow mass out and that interaction is violent.
No, not necessarily. You won't have ejection. Imagine a white dwarf entering a main sequence star, okay? So if it's just orbital energy, when it gets to the center and eject everything, you have no gravitational energy. You cannot eject it. The white dwarf will accrete mass and start to have burning on its surface. You form a giant, and then you jump to the AGB. It depends on the white dwarf. It's a CO white dwarf. So in this way, you cannot eject it. And we did the energetic of this because we were interested in a common envelope of a giant star that swallows a white dwarf and a main sequence. And because of dynamical friction inside the common envelope, the white dwarf gets into the envelope of the main sequence, but it cannot eject the material. Eventually, the core of the giant can eject the material, so we call it a parasite common envelope, because the ejection of the white dwarf on the main sequence is done by a third star. This is a red supergiant or whatever. So the energetic is very interesting. You cannot eject it by itself. So there are common processes, but some big differences.
Big differences, yeah.
You don't have a core.
All right, so we are way over time, and I apologize for that. That's probably my fault, and breaks my heart to stop the discussions now, but let's have the 10-minute break, and then if we still have time after the next 3 talks, we have open discussions after the entire session. So please hold your question until then, your general question, or just post them on our chats. And I'll see you in 10 minutes, so 44. You say something? Kai, can you please say something? I cannot hear you yet.
Hello?
Yes, now.
Hello, Tomek.
Yeah,
can you see my slide?
I can see your slide. I can hear you. I don't see your face, but it's up to you whether you want to have the camera on or not.
Yeah, I'm in the home.
Okay, all right. Please start.
Okay. Hello, everyone. I would present the observations of a peculiar luminous red nova 802018 HSO. So I'm Yongzhi Chai from Tsinghua University. Okay, so first of all, let's look at this map for the transients in the local universe. The x-axis is a time scale. The y-axis is the peak luminosity. The gap transients refer to the transients located at this region, which are populated by the ultrafine supernovae, the LBV outbursts, intermediate luminosity red transients, namely IOTs, and the luminous novae. All of them are poorly known, both the physical mechanisms and the observational features. So in this talk, my focus is on the luminous novae. Okay, we went through 09. This object, previous speakers have discussed a lot on this object. So here I just show it, and I would say this object is well studied and well observed red nova. Then here I show the photometry and the spectroscopy for the luminous novae. From the right picture, we can find the luminous novae show double peak light curve, and the first one is very sharp. The second one usually blue, usually very shallow or even a plateau. And from the spectroscopy, we can find that their spectra show tremendous change during its evolution. And at the early time, the continuum is very blue, then evolved to G2K type. Finally, it became M-type star. And we can find the tremendous change of H-alpha profile from very prominent, then weak, finally prominent again. At that time, we can find the blue shift of the H-alpha profile. And the most important thing is that we can detect the molecular bands. Okay, so in this picture, summarized the luminous nova scenarios. For example, the single one or the binaries. Okay, but more evidence supports luminous novae are originate from the stellar mergers. Okay, after this, we believe the luminous novae are originating from stellar mergers, but the intermediate luminosity red transients are from electron capture supernova explosions from super AGB stars. So there are different subclass of the gap transients and following different mechanisms. However, they always be confused, particularly at the early time. For example, let's look at this picture. The first 20 days, they have similar light curve. At the right picture, we can find their spectra for the luminous novae and the IOTs are very similar, with the prominent HR Balmer series plus some chasm lines. And in this talk, I want to report the observations of a peculiar luminous nova 802018 HSO, which shows traditional properties between IOTs and luminous novae. Okay, let's see this object. This is light curves. We can see the light curve. The rise time is around 1 week. The peak magnitude is around -14 mag. The peak luminosity is around 10 to 41 arc per second. The first peak is very prominent. Then the second one is a bit shallow and broad. At the bottom panel of this picture, I also compared HSO marked by the red squares, and comparing with other double-peaked luminous novae and the single-peaked IOTs. So from the light curve, this HSO is intermediate between luminous novae and IOTs. This picture shows the spectral evolution. So at the early time, we can find the blue continuum with black body temperature around at 1000 and at 100 Kelvin. Then evolves to very red with a temperature about 2000 Kelvin. And we can find the tremendous change of H alpha profile from prominent, then disappeared, then prominent again. At the late time, we also find the blue shift of the H alpha profile with a velocity of about 3 to 400 kilometers per second. And the last spectrum was obtained by the 10.4 meter telescope, GTC telescope. We can clearly find the molecular features here. So this, so here I show the comparison between HSO and the IRIS and the luminous nova GFS. So at the early time, first one is the early time, we can find they are similar, but during the middle time and the very late time, HSO is similar to luminous nova GFS, but very different from intermittent luminosity red transient 70B and 0 ATS. Okay. There is another object, AT2019 ABN. This object is another controversial one because we can see that the calcium-2 forbidden line of ABN is very weak from early to the late time. And at that time, we didn't find the molecular bands for the ABN. So ABN is very likely a peculiar intermittent luminosity red transient, not a luminous nova. We also study the SED evolution of HSO from the temperature that decline monotonically, the bolometric light curves of luminous novae and the IRIS. The dashed line marked by the dashed line indicates the IRIS. The solid line indicates the luminous novae. So the most interesting feature is the radius. We can see the luminous novae and the IRIS are significantly different. The luminous novae increase, but IRIS contracted with time. So from the radius evolution, probably this can be a diagnostic tool for discriminating luminous novae and IRIS. In addition to the photometry and the spectroscopy, we also investigate the Hubble Space Telescope archive images. This image was observed on 2004 November 70. So it's about 15 years before the man outburst. There is only a single detection in this band with absolute magnitude of the I band about -8 magnitude. So this is consistent with another luminous nova in M101. Okay, so what is the nature of 2018 HSO? From their traditional light curves at the SED diagnostics, the tremendous change of the spectral evolution. We also study the physical parameter correlations. For example, in the velocity, in the luminosity versus velocity diagram, the luminosity versus time decay diagram. So the parameters of HSO is located in both in the luminous red nova region in both diagrams. From the progenitor detection, there is a pluribus progenitor detection, which is similar to another luminous nova in M101. So combine all of them. So this object should be a peculiar luminous nova, hence originate from a common envelope plus the possible final merge scenario. Okay, thank you. As an observer, I just reported what I observed and what I measured. So I would leave the theoretical interpretations for theorists. Thank you.
Thank you very much. Let's wait a moment for questions or raised hands. Anyone? Of course, the questions may come later, and then we can ask them at the end of the session. So Kai, thank you very much for your talk. If you can stop share now.
Okay, thank you.
Thanks. Our next speaker is Vinaya Balsan. Vinaya, are you ready to share your slides?
Yeah.
I can see you, I can hear you, and I can see your slides now.
Okay, cool.
Yeah, now they're in full screen mode.
All right.
So yeah, whenever you're ready, start.
All right. Hi, everyone. Myself, Vinaya. I'm a grad student at University of Wisconsin-Milwaukee. So here I am presenting my work on a simplified framework to compute the observational appearance of CEE simulations. This work is done in collaboration with Logan Prest and Philip Chang in UW. All right. So we all know that CEE is an important process in binary star evolution. And have you observed CEE? We're already having so many discussions on this, but I'll briefly go through this anyway. So observationally, there is a 6 magnitude luminosity gap between the brightest novae and the faintest supernovae. And I'll use the term intermediate luminosity optical transients to refer to all those transients observed in this luminosity gap. And over the last decade, observations of these transients suggest that at least a few of these are stellar mergers, results of stellar mergers. And a possible example is V1309 Scorpii. However, a connection between these observed systems and numerical simulations of CE has not been made. So my goal is to develop a simplified framework to compute the observational appearance of CE from hydrodynamic simulations. So the idea we use here is the radial leakage of radiation from the expanding shell. So starting from the radiative transfer equation, we can write down a simplified order of magnitude equation for the moment J, with V is the expanding velocity of the shell and tau is the optical depth of the shell. Now consider a photon going through random walk within the shell. The photon will have an effective speed of c divided by tau. Now if the expansion velocity is greater than the effective speed of the photons, this term, the advection term dominates. The advection term dominates. And the photon gets trapped inside the shell and loses energy by adiabatic expansion. Now, if the photon is faster than the expanding shell, the photon can escape the expanding shell. So an observer starts to see photons coming from tau equal C over V boundary and beyond. So the method is to find tau equal C over V surface from the purely hydrodynamic simulations of CE. So to do this, we consider a sphere around each gas particle in the simulation with the size based on its density and mass. And we use simple geometry to find the distance traveled by any given light ray in the simulation through these spheres. And with that information, we can easily find the tau equal to C over V surface and the effective temperature of that surface. And from that, we can get the luminosity. In principle, we should be using Voronoi cells from the simulation instead of these spheres, but this approximation to spheres works because the Voronoi cells in the moving mesh simulation that we're using are close to spherical. Okay, so the system that we're testing this method now is a merger of a 2 solar mass red giant with the 1 solar mass companion. The red giant starts at a radius of 50 solar radii, and the companion circular orbit starts at the surface of the red giant. And this shows 100 days of the simulation. Yesterday, Logan already talked about this simulation. All right, so testing our method on this, note that this work is still in its preliminary stages. So here are a few preliminary results. I'm plotting the luminosity, the radius and temperature of these systems. You see that the luminosity is increasing. I'm plotting day 100 to day 250 of the merger. Luminosity is still increasing with some scattering. Radius seems to be consistently increasing with not much scattering, and the temperature is almost constant but with significant scattering. So in the near future, our plan is to refine our method and the simulation to better estimate the temperature, so that we can reduce this error in the luminosity. And what we see here is that the luminosity magnitude is in the range of other possible intermediate luminosity optical transients. All right, and the future plan is to do a parameter study of how the system parameters like red giant mass and radius changes the light curve, and of course compare our results with the light curves from real observation and trying to match our simulations with the real observations. Well, I guess that was quick. That's all I have. Thank you, and I'll take questions.
Thank you very much. Do we have questions to Vinaya or the previous speaker, to Kai? Yes, Morgan has a question.
Hi, thanks for this really interesting talk. So if maybe can we look for a second at your plots of the radius and temperature and those quantities? So I guess I'm curious how we're treating both the thermodynamics of the gas in these cases. Like, is it the ideal gas equation of state, or is there cooling involved in the simulation? So in a sense, we're looking at how the light will leak out, but have you been allowing that to happen dynamically as the simulation is running, or is this kind of a post-processing purely?
This is purely post-processing. The simulation that I'm using is the exact moving boundary simulation that Logan talked about yesterday.
Yeah.
And all these are purely post-processing of the simulation.
Okay, so there's not a cooling term, for example, a radiative cooling term in that model?
I assume there is no. If Logan is there, maybe he can comment more on that.
I didn't think so, but
okay.
Okay. Yeah, I mean, this is amazing, and I think it'll be really interesting to understand whether these effects are dynamically important and how those affect the sort of temperatures and stuff that
yeah, I mean, I would be interested in.
But building the methodology is the first step towards being able to do those experiments. So I think this is amazing.
Logan just wrote on chat that it's idle gas, adiabatic cooling, and no radiative transfer.
Right. Thank you so much.
Vinaya, do you see any difference depending on the angle from which you look at this system?
So these are basically considering a spherical symmetry and averaging over what I see. So at this point, I'm not considering any particular angle at which I'm looking at the system.
But eventually, that would be an option, or
that can be an option. Yes. I mean, I can send rays at any angles, but these results are considering this symmetry.
Gotcha. Yeah. Thank you. Noah has a question.
Yes, this is a very important work, and I really congratulate you for this. And I follow what Tomek said. I think the non-spherical effects here, this is my view, are huge. And I think more than the simulation, you should also consider inflation of bipolar lobes by jets, which I think are very important. If you look at the image I took from Tomek paper and put it on Slack, and in some very energetic supernovae, I think also we have two lobes on two sides of the equatorial plane that can change the light curve. So I really encourage you to look into non-spherical effects, but not only of these simulations, but go with the assumption that jets can power the event, as you know, we have in CK rule that Tomek studied in detail. So,
yeah, I will definitely consider those more complicated systems.
All right. Thank you very much, Vinya. Then I think, oh, sorry. There is still Alexei raising his hand. Alexei, please ask your question.
Thank you. Just a short question. I look at the simulation and I just wonder, does the center of mass drift to the top right?
Oh, I'm sorry. What was that?
So in the simulation, does the binary move with some velocity to the top right, or is it just an optical illusion of me? It seems to be.
It does move too.
Is it because of the initial setup, or is it because of some other physics?
Logan, can you comment on that?
Mass ejection asymmetry.
Yeah,
the
mass ejection is asymmetrical, so it just gives the center of mass of the binary a non-zero velocity.
So the remnant will be moving with real physical velocity, or is it just a numerical artifact?
No, it should be a real physical velocity.
Well, I mean, we get kind of like 0.5 AU over some 100 days, which is quite a velocity.
Yeah, that's really large. Yeah, we don't usually see that, but in this particular one, maybe there was a particularly large tidal tail at the beginning that just gave it a big kick.
Okay, interesting.
Okay, thank you, Vinaya, once again. Let's move on to our third and last talk of this blog. Roger, are you ready to share your slides?
Hi, yes.
All right. I can see you, I can hear you, I can see your slides in full screen. So whenever you go. Whenever you're ready, go.
Great. Thank you all for having me. Common envelope events are perhaps the most likely driving mechanism behind luminous red novae. And some of the best evidence that we have for this is the system V1309 SCO, which erupted in 2008 and showed a binary variability in the light curve prior to the outburst. I show on the left here just a simple animation of two rotating circles to just give the idea on how that binary can be seen. The light curve has the characteristic plateau shape of luminous red novae, and the remnant still remains hidden by dust. We want to try to simulate this target because it's some of the best observations that we have. So we do that by first creating the donor, and we evolve a 1D MESA model to the base of the red giant phase. I show the evolutionary track for that on the right. We choose the parameters that are set by the Stepien 2011 paper, which has a list of plausible donors, plausible binary configurations, actually. We create a 3D model, several 3D models using Star Smasher. It's a smooth particle hydrodynamics code. And we build the star using the MESA model, and we do it in 3D, and we place particles on a close-packed hexagonal lattice. We then let them interact dynamically until the total internal energy and gravitational potential energy of the envelope oscillates on a scale of less than about 10 to the 45 ergs. Star Smasher has an input parameter called NNopt. This is a parameter that dynamically controls the number of neighbors. In this way, it reduces artificial shocks that come about from particles that that are from very different mass resolutions, such as during the onset of the common envelope phase. We choose 3 different particle resolutions: 100,000 particles, 200,000, and 300,000 particles. And we calculate the integrated total energy profile, and we compare that to that of our 1D model. And we compare it in the top 0.1 solar mass of the envelope. In previous simulations of the same binary configuration, it is seen by that about 0.06 solar masses will be ejected from the primary's envelope, the donor's envelope. And on the right here, I show in many different colors the different values of N naught and the integrated energy profiles. It's actually the residuals, the 3D minus the 1D. In black are highlighted the optimal choices for N naught that we found. These are the ones that minimize the sum of the squared residuals. We find that our optimal models match the 1D to within 0.1%. In order to get the light that comes out of our simulation, now that we have the model, we can try to merge it, but first we need to figure out what is the light that will come out of our simulation. So we solve the radiative transfer equation with local thermodynamic equilibrium assumptions. And we receive the 2 equations shown on the top, one for effective temperature and one for the optical depth. One way to go about solving these is by using ray tracing. So we take a ray and we throw it into the simulation and we integrate along that ray to solve for the effective temperature and the optical depth. In order to calculate quantities along the ray, we adapt an SPH method by so SPH usually requires that there is a particle at the location where a quantity is being calculated. We relax this restraint and just choose any location and then say that the number of neighbors at that location are the number of particles whose kernels overlap at that spot. So it's similar to SPH, but not exactly the same. The result is effective temperatures that are about 2 orders of magnitude larger than what we expect. We also see that the optical depth is really high in the surface particles, and we show that in the top panel. Now, this is a problem because with ray tracing, the number of neighbors that are at any given position is never guaranteed. It is guaranteed the number of neighbors in an SPH simulation for an SPH particle, that is guaranteed, but at any given location, the number of neighbors there is not guaranteed. In fact, it's equal to 1 on the very first integration step, always for all rays. In order to quantify how the accuracy of our ray tracing method compares to the expected accuracy of the SPH code at that location, we compare the number of neighbors at the location R sub z to a quantity, where that quantity is the average of the number of neighbors that the surrounding particles have. So the particles whose kernels overlap at that position, we get their number of neighbors and then take the average. If eta is much, much less than 1, then the accuracy of the ray tracing is much worse than the expected accuracy of the SPH simulation. And if it's about 1, then it's comparable. But you only get that comparable accuracy deep within a simulation. And that's true regardless of what you're simulating. It could be a star, it could be a merger, it could be some water. It doesn't matter. The value of eta is always going to be about 1, only deep within the fluid. And so this particularly becomes an issue when the optical depth is really high near the surface. You can see in this plot on the right that the value of the integrated flux becomes set at very shallow depths. So this is well before eta can get anywhere close to 1. That's why the ray tracing solution is 2 orders of magnitude off. Our solution to this is what we call envelope fitting. We replace the unphysical density and the temperature distribution with MESA models. We generate many MESA models and all throughout the HR diagram, and we we calculate values of nabla, which is the slope in the log p log t space between a given position and the surface. These solutions are unique in their surface gravity and effective temperature. And so given some SPH particle, we can use its values of the local gravitation, the local gravitational acceleration and the temperature to fit it to one of these envelopes. And then we trace that envelope to the surface to get the effective temperature. A similar idea to this was done by Galovitz et al. In 2017. And they use an ideal gas and an adiabatic pressure to replace that unphysical density and temperature distribution. In the plot on the right, we show our particles, and the blowout panel on the right, those are our surface particles. And this black line is going from one of our surface particles out to where we expect the photospheric pressure to be. And you can see that the result is an effective temperature that's much lower than the actual effective temperatures that we get by tracing our models to the surface. The colored lines are some example models. Our result is effective temperatures that are within a few % of the expected effective temperature from the 1D model. We also see this strange star shape looking pattern in our 200,000 and 300,000 particle stars, and this is likely a result of the initial HCP lattice. We see something similar in 2D SPH with initial Cartesian grid. Finally, we take our 300,000 particle star, our best one, and we take it to Roche lobe overflow with a 0.16 solar mass point mass accretor. And again, 0.16 comes from the Stepien 2011 paper. This is in the pre-outflow stage. So this is well before, I shouldn't say well before, I don't have enough information to say that, but this is before mass transfer at least. If we look at the variability in the magnitude of the star as it rotates on just the orbital plane, then we get a variability that is about 0.3, which is comparable to that of V1309 SCO prior to the merger, or prior to the outburst event. We hope to, in future simulations, do a full dynamical simulation to capture the outflow and subsequently calculate the full light curve of the common envelope event. Thanks.
Thank you very much, Roger. Questions? So Roger, in this very animation that you're showing, it seems that we see only one lobe, right? Where the second star is not here.
That's right. The second star is not visible. That's only because it's a point mass, and point masses in the SPH code interact only gravitationally with the other particles, so they're not really considered as fluid.
Gotcha. I'm still waiting for questions from the audience. Those questions may go to all the three speakers of this blog. Anyone? Maybe people are tired after the first hour.
Should I stop sharing?
Yeah, I think, yeah, we can always pull it up if someone asks a question later. Let's open the floor for general discussion about mergers, transients, and related phenomena. Is there anyone who would like to raise any particular topic? Please raise your hand. I prepared a few discussion points. Completely, this is a very subjective and probably very far from common envelope, hardcore common envelope questions. But if anyone wants to comment on any of those points, I would be very happy to hear what you have to say. Noam, you have your hand raised. Please go.
Yes, I would like to make a point that one of the participants here is Romek Tilenda, and he's one of the old and wise people here. And I mentioned already Howard Bond and Bruce Balick, people who are really started to publish a long time before we entered the field. And it's important to see them here for the continuation. And I personally thank Romek for bringing me to this field of transient object when I visited Torun in 2002, and he told me that there's an interesting star erupted here, VH38 Mon. He thought about planets entering a star at the beginning, which also can take place, but it wasn't energetic enough for this particular object. And then we came with the idea of merger, which actually was first the idea of Romek Tilenda, and I'm really happy to see him here, even if he didn't participate till now. That's what I wanted to say. You are mute, Tomek. We didn't hear you.
I'm sorry. Gloria, please ask your question.
Yes, I'm sorry if this is a silly question, but given the fact that after the outburst of V1309 SCO, there is so much occultation to the central source, I was wondering, are we absolutely 100% sure that the two objects merged? Or is there a small possibility that a large envelope was ejected and the in-spiraling was stopped? Is there any, I mean, that's why I'm asking if it's a silly question, because it may be a silly question, may be obvious, but I don't see the answer. Thank you.
Thank you, Gloria. I'm not sure if you were here for the previous block of talks when Laura asked a similar question.
I apologize. I was teaching my class. I had to log out. Sorry. So if the question is answered, that's okay. Then
there is discussion. Fortunately, we have a record of it partially on Slack. So if you would like to follow on that on Slack, that there is some discussion about that in particular.
Okay, thank you. I apologize. Thank you.
No problem. Do we have any comments, questions about mergers? Nadia.
Yeah, my question is like from the observational point of view, we see that many of these transients share similar properties, right? We have like LBV eruptions, we have these ELOTs which have obscured progenitors, we have luminous red novae. So I'm wondering how can we advance, right? Because we see that some of these transients share like common properties to like one family or the other. So what can we do, you know, to maybe like gather more information about the origin of these transients, or, you know, they seem to be like mixed. There is no clear boundaries between them. So like, how do we face this problem?
Yeah, exactly. And how to recognize a transient that is going off at the moment, whether it's interesting to follow it up or it's just another of the common eruptive objects. That's a very interesting question.
Right. I mean, as an observer, at the end, you have to pour like resources, right, into a transient that you don't know whether it will develop into luminous red nova or if it will be like one of these CLRTs or something like that. So, I mean, any, you know, ideas would be really welcome. Thank you.
Well, so far, the solution is to follow everything, right? But at some point you run out of resources.
Right, we need more benevolent tax to our proposals.
Right. Hagai, would you like to ask your question or share with us your comment?
Yeah, just a short comment. At least for stellar mergers, and these main sequence stellar mergers, right, require a very close binary star. Right, it's not following the evolution of the star, just merge from whatever reason. Now, we know from observations that basically all, or at least above 95% of all close binaries have third companions. Do we know is that this is the case, that all the cases we see a merger, we might have an evidence for, well, now a secondary, originally a primary companion?
Everyone is welcome to reply, but if from what I know, the galactic systems that we studied, there is only clear evidence of a third body in VA38 monocerotis, and there was a talk earlier today about the architecture of this triple system before the merger, but that's a very wide binary, wider than 250 astronomical units. So it's unclear whether the third body had any doing in the merger process. For the other ones, it's very difficult to prove that there isn't a third body, right? Those objects are usually at kiloparsecs distances, so very hard to observe. Anyone would like to follow up on this? Maybe Morgan, you were raising hand to.
I guess I was going to follow up on Nadia's point. So if other people want to talk about this first, I should go ahead.
No, Morgan, please continue with the topic.
Yeah, so I wanted to ask Nadia whether something that I'm not an observer, so I'm not making these decisions, but it's clear to me that obviously it's really beneficial if you can make the decision based on like the earlier data, like the sooner you can decide whether to continue following an object, presumably that's beneficial for your overall use of resources. And I was wondering if you could comment on whether the approach that you've been taking in extragalactic systems, looking at the progenitors in detail, do you think that's going to be a promising distinguishing characteristic? So like, for example, say you discover a new transient and you look at the history of its progenitor over the preceding decade, do you think that will give you information that you can make decisions on?
Well, definitely, like one of my approaches is actually to look if there's any progenitor detection by HST, for example. So if there is any evidence that's like, for example, a yellow supergiant, that gives you like way more points for it to be a luminous red nova later on. But yeah, for many objects, we still don't have the HST like archival information, for example. So you don't know whether the progenitor kind of sits in the LBV region or not, or maybe it will be like an ELRT as well. So you need to wait for those like forbidden calcium lines to develop maybe like later on, or wait for this molecular absorption to occur also like later in the life of the transients. That will tell you that's a luminous red nova. So yeah, unfortunately, like, you will need to spend like at least some follow-up during the first couple of months probably before the transient becomes redder and redder for a luminous red nova or not for some other transients. So yeah, I would say like definitely archival data, if it exists, it's a strong point for a follow-up if, to select that source. So yeah, I have some projects, to actually use that into develop a selection strategy for these transients.
Oh, fantastic. Thank you.
So a few talks today touched the problem of the light curves. We see the very different very similar and also very different light curves. Sometimes we see only single peaks, sometimes we see 3 peaks. Is there a unified explanation of why we see those different peaks? Maybe Andre, you would like to summarize what happened and what you take from today's talks?
Yeah, so why we see I would say, I can answer why we see plateau or 2 distinct peaks. And I think that just depends on the density profile of the pre-existing material. So, and on the properties of the ejecta. Why we see 3 peaks, I don't have a good explanation for that. But at this point, I don't have, regarding the plateau or a second peak, I don't have a, like quantitative proof in my hand. because we are just starting to do the models, as I was showing the 2D hydro at the end.
Noam?
Yes, in Eta Carina, the eruption in 1837 to 1856, we see several peaks, 2 clear peaks, but there might be indication of third and fourth peak. And Amit Kashi did the work, and this happens that and other people did as well. Gusto de Minelli pointed it first, but we modeled it as binary, and it seemed these peaks were the periastron passages of the present binary. We don't need a third star there. So sometimes if we see peaks, very clear peaks, they might be periastron passages. In my model, these are jet activity episodes. We see it in active galactic nuclei, the jets go in activity up and down and so on. So it might be, the accretion rate that dictates the power of the jets. This can be another reason for peaks, and also the merger process itself. There is a merger in eccentric orbit. It can enter, it can come closer 2-3 times before merger. All these can influence the peaks, as well as, yes, what Andrzej said, collision of ejector with previously ejected material.
I see raised hands of Gloria and Hagai. I don't know if this is from the previous question or if you still have a question, please go ahead.
Yeah, I was just going to comment.
Yeah.
There is a Wolf-Rayet binary system in the Small Magellanic Cloud called HD 5980. And it's also a triple or quadruple system. And in 1994, it underwent an eruption. The comment just made reminded me that in that eruption, there was also, one could call them multiple peaks. There was a precursor eruption, and then there was a secondary, much brighter eruption following the precursor. And the way we're interpreting these eruptions, because this is definitely not a merger, because you see eclipses and the eclipses are still visible and all the stars are still visible in the system. So it's definitely not a merger. And the way we're interpreting this is periastron passages causing tidal shear energy dissipation events, which destabilize the star. And of course, when you have these very bright luminous objects, you have the Eddington luminosity limit. And I think this is one important difference between the massive stars and the lower mass stars, in that if you have a massive star, it's just a little bit of excess energy that you can input, maybe during a periastron passage, will drive the system to be over superluminous, super Eddington, I'm sorry. And then you would get the eruptive event. I don't see this happening easily in the lower mass systems where the radiation pressure is much lower. So I think, in answer to two of the questions, I think there is a difference between the massive cases and the lower mass cases. And the other issue of the other periastron passage, where if you do have tidal shear energy dissipation being input into the star, you can cause an eruption. Thank you.
Thank you, Gloria. Andre?
Yeah, so I just wanted to follow up on your question, Tomek. I briefly looked up a paper that I would like to show. Could you?
Yeah, sure. Yeah. Stop sharing now.
Yeah, so I'm showing a paper by Tuguldur Suchbold and Todd Thompson, who look at type 2 plateau supernovae. So I think there is a potential for inspiration from this field. So what they did was they took a low luminosity type 2 plateau supernova that's shown in the dashed line, and then inside the ejecta they put in a magnetar. But that it's magnetar, that doesn't mean much. It's just a source of energy input that varies over time according to some prescription. And the colored lines above are the light curves that they got after considering this additional energy source. So in my mind, like the original light curve had a quite nice plateau, but the modified light curves seem to have a second peak. So, and yet at the same time, there would be probably little evidence for this, say, extra energy source when looking from outside, because everything is hidden by the hydrogen envelope that is expanding. So I think this can be translated as a principle to luminous red novae, that there might be an embedded source of energy, say the shock interaction, and how exactly the light curve comes out needs to be determined with more detailed modeling that takes into account opacities, an equation of state, and line of sight, etc.
Thank you, Andre. If there is no follow-up on this, I would like to raise one last point from my list. So when I studied the galactic merger remnants, it seems that we see a lot of lithium in most of them. And lithium, of course, problematic, but can be explained in the remnants in many different ways. For instance, in V3 monocerotis, is maybe related to the fact that the primary merged with a pre-main sequence star, which had intrinsic amount of lithium, and that stayed in the atmosphere of the object that we see now. But another way to produce lithium is similar to that we know in some red giants, RGB stars. This is the Cameron-Fowler effect related to the mixing in the atmosphere, in the upper atmosphere of those stars. So I'm wondering whether the modelers who attack the problem of common envelope can actually test whether there is some extra mixing that would produce enhanced amount of lithium that actually can be observed in the spectra of those objects that are expected to be recent merger remnants. Is that possible? Is that feasible? Paul?
It seems like that might be even harder than doing the convective energy transport correctly.
I was afraid someone would say so. Andre, you still have your hand raised. Would you like to say something? Andre, do you want to say something? I see your hand up.
Sorry, that's a leftover from.
Oh yeah, okay.
Sorry.
So I think we ran out of time now, and I see Noah messaged everyone that we should start 20 minutes later because of this longish session now. So I'll see you in less than an hour. So take your break and come back